Hello. Right, welcome everybody to today's session, looking at unlocking AI in engineering. I'm Alex from SimScale. I'll be your host for today's session. And we're here today with guest speakers, Generative Engineering, to explore the world of AI augmented engineering and simulation workflows and what it means to be AI ready today. So the first speaker you'll hear from will be David Heine. David is co-founder and CEO at SimScale, where he is committed to empowering every engineer to innovate faster by making high-fidelity engineering simulation truly accessible. He holds degrees in mechanical engineering, mathematics, and computational science from Georgia Tech and TU Munich. So hello to David. We're excited to be joined by Lawrence Cook. Lawrence is co-founder at Generative Engineering, where he holds the where he leads the development of next generation design space exploration and collaboration tools for complex engineering. He holds a PhD from Cambridge University and brings over a decade of experience in computational engineering from academia to industry. So we're going to get started right away. Please feel free to submit any questions that you have as we go along in the Q&A panel. You should see a questions panel in GoToWebinar. We will include these in the Q&A session at the end of the main presentation. So without further ado, David and Lawrence, the floor is yours. Over to you.
Thanks a lot, Alex. And also from my side again, hello everyone. Excited to be here, excited that you join us, and me and Lawrence for this 30-minute session. And also, we just talked with Lawrence before in the preparation here. We forgot to send a memo to Lawrence that we're going to wear checked shirts today. So unfortunately, we missed that part. But other than that, we're well prepared. We try to be sensitive to your time and go into medias res right away. What Alex alluded to already a minute ago is what we are trying to achieve today is a bit. Everybody in the audience today is already using SimScale, has already deployed SimScale to various degrees into their engineering workflows. And we at SimScale, we've been building SimScale from the get-go for a future where AI will be used to interpret past engineering data to accelerate or automate future engineering decisions all along. But the rate of progress we've been seeing over the last 2 years, 1.5 years, is also mind-blowing to us. And we're really sort of every month at this point are excited about the progress that's happening in the AI world at large, but then also how we can leverage it, and specifically because SimScale customers and SimScale users have been generating data in a way that's already accessible to AI and can be leveraged AI. Also, how SimScale customers can leverage it, and so hopefully by over the next 30 to 40 minutes, we will have achieved 2 things. One is how the SimScale AI infrastructure works and what you can do with it already today and what you will be able to do with it in the future. And then I'm excited that Lawrence from the Generative Engineering team is joining us because they're doing exciting work around how to leverage the fact that you can suddenly run simulation much faster and much or in a more automated way, and you can start exploring the design space with new technologies. And so Lawrence will show us what his team is working on in a second, so unlocking the next generation or new engineering workflows. And then we'll wrap things up with a quick Q&A, and we hope everything that we cover is not just interesting, but also relevant for your engineering work. I'll keep this short. Everybody in the audience is already familiar with SimScale. I believe at the core, SimScale is about helping engineering teams innovate faster. And I think you're aware of that, which is why quick company introduction. Over to Lawrence. Over to you.
Thanks, David. So we at Generative Engineering are trying to massively accelerate engineering design, essentially by making generative algorithms that previously were reserved for experts and people in niche fields accessible to anyone, from pumps to vehicle chassis to building facades to aerospace applications and automotive, which is some of our background. Basically, anything you can simulate, you should be able to generatively design, and that's why we're interested with SimScale. So great to be here.
We agree with that, that statement. Good. Then let's jump into it. 4 to 5 slides on our thinking around AI, and then I'll show 2 to 3 just small demos to give you a gist of what we're working on. And this is a bit, this little, I guess, visual here is a bit of a provocative statement of If you think about it today, every engineering team or most engineering teams are already using the large transformer models, ChatGPTs, Claudes of the world to generate text, to generate images, to generate code. But why are we not using it yet for core engineering workflows as mechanical design, mechanical engineering, generative engineering? And I guess the reason is obvious. If you think about it, the large transformer models that are around that are already in general purpose use are trained on terabytes of text data and terabytes of image data that is broadly applicable. Unfortunately, there is no equivalent of that of large public data sets around engineering data. And even if it would be around, the second question is like, how high quality is that data? Does that data, whatever is fed into that transformer model, is that actually suitable to your organization's engineering needs, et cetera, et cetera? So the question is, will there be at some point a large AI model that actually transforms prompts into engineering design? Could be, really. I mean, we're not saying like that future can't happen, but we believe what's more imminent, what's having an impact today is where not the entire workflow is automated with an AI system at large, so from sort of intent to finalized design, but rather what we see emerging is many interesting companies, many interesting teams working on certain parts of that workflow. And there's interesting work being done along all of the spectrum of an engineering process, from more text-based requirements data, from 3D generation, from the simulation-based drawing. There's many interesting companies that are doing interesting work in this field, and SimScale per se, and that's what we're seeing. What you see here on the right is we're focused on the process part where a design is being generated in some shape or form by a generative workflow, by an AI, by a human, and then until it's evaluated, that cycle, this is what we set out to sort of accelerate and automate. We're going to see it in action in a second. But that then, from our point of view, unlocks the ability to explore design spaces differently, to generate designs differently, where generative engineering is just a great example of the work that team is doing. And the reason why we're focused on that specific part is because we believe, or we're seeing at the day-to-day basis in our customer base, that the time it takes an engineering team from the design being generated to a design being simulated or evaluated, that is a fundamental rate-limiting factor for how fast an engineering team can move and how fast an engineering team can innovate. And if you double-click on this, many teams are familiar with the solve time. So we call it the simulation cycle time, as if somebody presses somewhere on solve, and then sort of a simulation runs up, and we know it can take hours, days, sometimes even longer. And that is a part that needs to be accelerated. But then the bigger part, really more often the bigger part, is not the time where a simulation runs, but actually the time an engineering team waits until somebody starts to run that simulation. And that's the bigger chunk is what we call the simulation lead time, which is typically the dead times between engineering handoffs, Outlook, emails, phone calls. That's where a lot of time is lost. And we believe compressing that will unlock close to a workflow that we've seen at the top, as in like from an intent to a finished design. If we can really speed that part up very, very fast, we're getting close to something like sort of prompt engineering, something to where AI can be used as a core tool in mechanical design. And the way we think about it, and Lawrence will show an example later, is every engineering problem, every engineering task, in some shape or form can be stated as an optimization problem. So some piece of equipment where you maximize for certain objectives, subject to certain constraints. And typically here, we'll see Lawrence later showing lots of examples around rotating equipment. So here we have the pump example, where the typical problem statement is you have a certain head you want to achieve, a certain operating point, certain flow rate, and of course you want to maximize the efficiency of that pump, that you need as little energy from the motor as possible. And so what happens typically, an engineer doesn't start from scratch, but sits down, takes some design from somewhere, starts a manual design, makes some tweaks based on the latest requirements, and then some other engineer typically evaluates the design. And that's sort of the cycle. Depending on the project, you have a limited amount of those iterations at your disposal to actually get a design right. And really, this is equipment agnostic. This is engineering task or product agnostic. Valves, cold plates, solenoids, just some examples here. It doesn't matter what examples. You can almost break it down to this iterative process where design generation, design evaluation, in an iterative fashion tries to approximate actually the requirements you're set out to solve. And as we've heard the slide before, from our point of view, like SimScale sets out to solve two bottlenecks in this. The first one, the obvious one, is cut down the time the actual simulation takes. Deep learning surrogate models for that, or these days we're calling it physics AI, is at the core about using past simulation data to predict future simulation results, but in seconds. Right? So this technology has been around for a number of years, but now thanks to an infrastructure that SimScale provides out of the box, it becomes much more attainable because the data management is taken care of, yada, yada, yada. We're going to see it in action in a second. But it's just part of the equation because, again, much time is spent to wait that somebody sits down and sets up the simulation, evaluates the simulation, documents the simulation. And that's really more the manual parts of that process. And the large transformer models these days and the ability to tune and teach them and configure them to interact with tools and software and data allows to actually now gradually start automating the manual parts as well. We're going to see it in action in a second. And we believe the combination of a high degree of automation and setup and evaluation of simulations together with the ability to predict physics in seconds opens up very interesting workflows. Right? And again, just like because we're going to hand it over to Lawrence in like 5 to 6 minutes, the important bit is like SimScale at the core solves the issue of like automating the simulation setup and the evaluation as well as the solve time. But then to navigate the workflows, there's like many interesting new workflows that are opening up, and generative engineering, I think, has one of them, and we're excited about it, and we're excited to see what Lawrence will show in a second. All right, now quickly to the basics and a quick sort of the fundamental technology that we've built at SimScale is, again, we'll take the example of the pump. When using SimScale, you're all familiar already with the ability to solve a certain application on SimScale, simulate a certain application on SimScale in a cloud-native way, with the benefits of being able to do it hardware agnostic, to do it globally, to do it collaboratively, to do it at scale, etc. So all the out-of-the-box advantages that a cloud CAE workflows brings. Now, as your teams are generating more and more data on SimScale, that data is automatically prepared to train physics AI models that has been around in SimScale now for a number of months already, where you can take a certain set of simulations, select them, train a deep learning surrogate model, and start predicting physics for similar geometries and similar simulation setups in seconds. We're going to see it in action in a second. And then the last bit, this is the latest piece of, or the second big engineering, the second big AI systems that we built at SimScale is the ability to now have a transformer model sit right next to your engineer and start interacting with the software automatically. We're going to see that in a second as well. And that is the part where it actually helps with the human, with the manual work that is involved in running a simulation workflow. And so the result here, before we jump over to the demo, typically sort of what most customers are looking for is in some shape or form business impact and engineering impact. And again, depending on the industry, because I know also today the audience is very much sort of industry agnostic from automotive, from industrial equipment, from electronics, from medical. So the business reasons is oftentimes different. But what engineering leaders are looking for at the end is engineering velocity. So by your engineering team moving faster, it might be that we'll see Lawrence later talk about, that you respond with higher quality to an RFQ in less time. So you can respond to more RFQs, increase the win rate for it, top line impact. It sometimes comes down to supporting legacy product lines with less engineering manpower or engineering efficiency. So you want to have the same output, but you want to have less engineering budget on it because you want to build up new product development and the like. So again, different reasons on the business side, but at the end, it's about engineering velocity. And the same on the engineering impact, the innovation impact. Engineering velocity allows you to explore more design versions, and as a result, better product in a shorter amount of time to market. That's typically sort of the reason we're seeing why teams are adopting this in the first place. Enough business speak. Let's see this in action for a second, and we'll really just like do a very, very quick walkthrough on those three sort of cloud CAE quickly once in action, because you all know it. Then how physics AI ties into it, and then a quick engineering AI example as well. Lawrence, could you do me a favor and just confirm that we're seeing a CAD model right now in action?
Yes, indeed.
Is that working? Yeah, that works. Okay, excellent, good. So just a very small example of, again, most of you have seen SimScale, I believe, and so the first step here, being able to predict being able to run a simulation completely without any hardware, just in a cloud and a web browser. Most of you have seen it. So the typical example would be, I have like a pump design. I have a different requirement because in some project something changed, and like as a program engineer, as a design engineer, I'm making certain changes, and instead of waiting now for the simulation team to actually give me back a result or an evaluation of that design, what I can do instead, I can hop over to SimScale, start from scratch, go into my dashboard, start a new project, pump, change, quick check, blank, new project. I'll bring in the geometry that we've just seen. And I can now use SimScale's data and process management capabilities to not set the simulation up from scratch, but actually apply a template that my simulation team has provided me with that we typically use for these types of applications. So instead of starting from scratch, I use the import simulation workflow. I go to the appropriate section of where my simulation team has provided me the template for. I import it. You can see it comes with a example CAD model. So this one has 8 blades and has a short outlet. The one we just imported has 9 blades and a longer outlet. Again, just a very simple example. And I'm going to swap the geometry to have it point to my new geometry. Because these geometries are similar enough, topological associativity is maintained, and I can kick off the simulation. All right, so far, this was mostly a repetition for most of the people in the audience. But again, as we now start more and more of these types of simulations, and more engineers are running similar simulations, or you might do a design of experiment, etc. So in whatever shape or form you start to generate more data in SimScale, you have now the ability to train a physics AI model. Actually, since a number of months, you have the ability to train a physics AI model. And if you invoke that physics AI model, then what's now happening is it's integrated in the exact same way, but instead of now doing a physics simulation using a finite volume solve, what we can see is that within a second, the CAD input along with the simulation setup is being used to predict physics with an AI inference. Hence, in seconds, we get a response. The obvious advantage of this is, speaking about engineering velocity that we've heard a second ago, I can now change the operating point, I can change the geometry. Because it's a parameter-free method, and I have now the ability to directly see real-time predictions and can sort of make changes, can bring in a new CAD model, predict it for that, etc. Again, that's something that physics AI has been in SimScale now for a number of months. On the right, maybe just also a quick note for the audience members that haven't seen it yet. There's the ability to evaluate how close I am to the training space. So if I'm leaving the space on which my AI model has been trained, I get a confidence prediction here on the right that prevents me from using a physics AI prediction that isn't reliable. So in this case, we can see the physics AI model has not been trained for this. And just to bring this point home, because we're deploying physics AI and the traditional CFD, FEA, thermal, Emacs solvers in the same environment, it's not a problem because I can simply, for this operating point, now also just kick off a simulation. And again, you've seen this simultaneous simulations as you see fit. Okay. Now, this was the points around, okay, we are in the cloud, we can run cloud workflows, we can do physics AI prediction out of the box as well. And now the latest sort of addition here is the fact that we can start leveraging the large transformer models to actually help me interact with SimScale and help me automate the manual parts of a simulation workflow. And for that, what you can see here on the right, that we're gradually rolling out. So this is already in production, enabled for the first alpha users. And what it allows me to do is we've configured a large transformer model to be able to interact with SimScale. And so this transformer model sees the geometry, so it is geometry aware. So we can say And again, there's an LLM behind it, and so that LLM basically is out of the box trained on the internet and sort of has a lot of understanding. So you can see, okay, it knows what a valve is. We can ask what kind of valve. Again, all of this you've seen. Now, this is sort of standard LLM, just like it helps me stuff. Okay, it understands this is a globe valve. Again, it knows engineering contexts, it knows how to interpret things, etc. You've seen all of this. What's now new is the ability to have it interact with the simulation software. So in this case, what I can tell it is, I want of this valve, including preloaded bolts. Use the labels in the CAD, because I might have enriched the CAD with a body or with model-based systems labels. Fully automatic, please. Okay, and so just to get a sense for what it does, okay, it understands intent, it knows how to use SimScale, it knows the basics about SimScale and simulation, and so now it starts reasoning through the project. It sees the topology, it sees, okay, what is in the topology marked. Now it understands, okay, I want preloads, depending on what it finds in the geometry, it will use those as labels to assign boundary conditions. There's lots of ways how now an organization can tune it. So it found the M5 and the M8 bolts in the topology. It found the internal pressure. Oh, we didn't set a pressure. So we should have said, there we go. Please provide the value in the unit. There we go. So it says, it just figured out that we haven't provided in the prompt the internal pressure. And again, as we are used to from an LLM, okay, we had 2 bar internal pressure, please. Otherwise, I can suggest common. Make an educated guess on the materials. And so on the materials, what I wanted to see is that, because in this case, we have a couple of the parts have been labeled with a material. And if it finds that in the material library, it's going to add it. We can see ABS because 2 parts have been labeled as ABS. The other ones have not been, and so it understands. Okay, it makes an educated guess. Valve steel, assign steel. Again, this is sort of an out-of-the-box example that that we put together here at SimScale. But the thing is, for an organization, etc. And so now this one, right? And this the same, and we can now run the simulation. Maybe another quick example, similar one would be that one. And Lawrence, then I'll be back in a second. And we'll see what Lawrence will do with such a workflow. But here's a similar story. We can see again in assembly, peak stress. So in this case, it again is topology aware. In this case, all materials have been assigned in the topology, and so it again reasons through it and sort of understands context, understands intent. The element that we're not seeing, like how to think about this, is to some extent as a junior engineer that can use SimScale, a junior engineer that knows the internet and can search the internet, but of course does not know out of the box how your specific team and how your specific organization's best practices function. This is then done in an enrichment phase, where as it understands how your simulations are being run, we're adding more capabilities to supply custom materials to the model to train it on, to really get it to a point where you can, at least to a certain extent, tell it how to approach certain problems, how to run certain simulations. And this is early days for these capabilities, but what we're seeing is that every month now, the materials, the large transformer models are getting better and better. And so they are getting better at reasoning, they're getting better at understanding intent, they're getting better at solving problems. Sometimes when I'm not sure if it now happened here, but sometimes it makes mistakes and it then corrects these mistakes. And so it's the fundamental ability to actually leverage the large transformer models to help you work through engineering workflows. And again, given the fact that SimScale is built in the cloud, that these models can be deployed this way, that you can tune it for the entire organization, that you have user and process management properly in place, allows you to basically deploy these models in a proper way. Right? And so to bring this one home is why we're excited about this is the fact that now that you've seen this in action, we're going back to this little graphic here. Is we saw physics AI, how you can predict physics in real time. And then we saw sort of the sense of engineering AI, how a large transformer model is now able, based on guidance, to set up and evaluate simulations, where we gradually can more and more automate the setup and the evaluation. And so both together remove a lot of the human and computational burden of the typically very elaborate simulation workflow. And by the simulation lead time thereby collapsing to a very short amount of time, new workflows open up, new authoring workflows, new generative engineering workflows open up. And that's why we're excited also to have Lawrence here, because Lawrence and the generative engineering team have one vision for how what this unlocks, and that's why we're now excited to hand it over to Lawrence and see how they envision these types of new capabilities to be leveraged. Lawrence, with that, I would give it over to you.
Yeah, thanks, David. There we go, show screen. You can see that okay?
Yep, that works.
Awesome. So like SimScale at Generative Engineering, we've been asking this question, which is what will AI in core engineering workflows look like? And like SimScale, we see a big opportunity for this collaboration between engineering AI and physics AI. So like David has just shown, there's massive opportunity for physics AI to speed up like the simulation time itself. But this engineering AI to automate the design and iteration, like it's quite broad. Like there's a lot of things involved in a design iteration loop. So we're focusing today on like a few specific things that we built on top of the things that David has shown that can really speed up this design time. So like being able to do what AIs are really good at, which is summarizing information and turning requirements into studies, and not just simulation studies, but optimization studies and automated studies. And to automate the setup and configuration. So not just the template simulations like David has been saying, but like workflows on top of that. And then to be able to like look at all the designs you can now generate and pull that out into a design improvement and a trade-off, because there's never really one optimal design. How can you come up with multiple and then still have the engineering judgment to be able to decide what direction to go in? And so to sort of frame this, we want to focus in on the design proposal route. And like David has been saying, this could be used for new product development, for an RFP. You could be trying to automate internal workflows, to generate optimization studies. And previously, if you wanted to do this, where the starting point was a baseline design, and you wanted to try and automate the getting to a proposal from this, you have a baseline, you've got to extract requirements, try to set up an automatic design space exploration, so some automated iteration loops, then produce hundreds of different designs, pick out an optimal, hopefully that's one that meets the requirements, and then you have a new design proposal. And if you want to do this previously, you essentially have to be an expert in scripting, in APIs, in machine learning, in databases, in writing reports and optimization algorithms. And as someone who in a past life spent months creating workflows in Python to do this sort of thing, like I know it can be super painful. And when people say leverage engineering AI, if this is what you have to do, it's not really very easy. So like David has been saying, there's a big opportunity for engineering AIs to automate a lot of the setup work required to do this sort of thing. And now with physics AI, for this loop to be much quicker. So we're trying to make it much easier and much faster for this design proposal automation to be possible. So we're going to show you what we built to enable this. And like David was showing, we've got the exact same pump model. So this is in CAD, it's the Onshape one. And like David was showing, this essentially extracts high-level input parameters. So any input into the system, you can use Onshape to essentially generate a new design. And if you wrap this in an automation loop, this essentially becomes a bit like a generative model, because any new high-level input, you get a new geometry. So what we can do now is we essentially copy the URL from Onshape into the generative platform, and this translates the Onshape information into a document, which does two important things. It turns this into something that the engineering AIs can reference. So again, like David was saying, they need to be CAD aware and understand what it wants to do with this CAD. But importantly, in our platform, this sort of extracts all the high-level input and output parameters and turns this into an executable function. So this is a cloud executable part of the platform that an agent or human or algorithm can go in and say, I would like a new geometry, please. Change the blade angle, change this, and vary this automatically. And we'll then store and track every single geometry that you ever generate with this. So this is the starting point. This is a baseline CAD, your pump that doesn't meet requirements, and you've been given a brief. Again, it could be RFP, it could be new program development. In this case, we want to design a pump for a municipal water supply. So we give it requirements on the flow rate and the head, and we want a high efficiency. And then our engineering AI agent does what AI is good at, which is researching the information that might be relevant to this pump design. You can look at the CAD, you can look at the information on the internet because that's embedded. You can look at any other documents that you've provided and say, hey, I think this is the problem you're trying to solve. So in this platform, we represent that as goals, which is essentially just a list of what it thinks the engineer is trying to do. But importantly, it tracks all the research that it's doing as a document too, because this is now more information that engineering AI's downstream can leverage. And we might pass this into the SimScale agent. And we get suggested goals here. So we've got the ones we set, we can edit them, but it's also suggesting to consider what other parameters might be important and start to consider things like cavitation, which you hadn't initially provided. That's all just from data available and useful for an engineer trying to set up this problem. But what we're focusing on is this can now collaborate with a SimScale agent. So it wants to set up a simulation because it wants to calculate the efficiency and the flow rate. And we've just seen that SimScale can do this in templates. And our agent trying to set up an optimization study says, hey, SimScale, set up a template that can find these parameters. So now this is saying within SimScale, creating a project, setting those inlet static pressures and then boundary conditions, using that geometry associativity that we were talking about, and then creating that template function. And this will look something like this. It's the same sort of template you can set up yourself, but it's just gone and set all the faces and set the conditions. And like in Onshape, extracted all the numeric parameters and a summary of the output and the numeric performance criteria and said, this is now part of a workflow you might want to run automatically. And it's trying to be nice, so it says, I did my best, but please tell me further. And I like, David, how you said please in all your prompts. So now this has got essentially a geometry generator and an analysis function that can be run automatically by anyone. And this pump is connected to the other function. So we've set up a workflow automatically, essentially removing all the barriers to entry to doing this before. So whereas previously to do this, you had to wrap APIs yourself, maybe buy everything in an all-in-one commercial package that's completely inflexible. We want to make this super easy for anyone to be able to do, especially if you're an engineering manager or like a product manager who would not normally be able to do the code, or you'll be bottlenecked on an expert doing this. So now we're connected to these functions, we're ready to experiment, and this is sort of now where the generative platform comes into its own. We have all these parameters here, we can start to optimize and try and generate design proposals that will meet those requirements. So just to summarize this little part of the demo, the key thing here is the agent-to-agent interaction, which is something unlocked by what David has been showing, and it's the future of how these systems are going to collaborate. It's not going to be one big engineering AI agent that spits out a pump. There's going to be all these different ones that are good at setting up studies, setting up simulations, extracting data, doing research, and we're building some of these that collaborate. And this essentially gives you, with plug and play, zero setup, a connected set of cloud executables that you can use to generate designs. So then what can we do? So now this is available for anyone to go in and start setting up studies. So the point here is we've got a design brief and we want to generate different pump designs that will meet those requirements. But we want to define the problem. So here we can go in and say, I don't want you to touch things like the input and output pipe lengths because they're part of the problem, but blade, anything to do with the blade, please can you explore that? So I've added one input here. I'll go and search through, find the other inputs, and just set up a problem super dynamically. And as you can see at the bottom there, you can always ask the AI to do some of this for you. So we're going to leave pipe length constant. We are going to vary the blade radius. We are going to vary the angle of the diffuser because that's something we have a little bit of control over. We don't want to touch the fluids. We do care about rotational velocity because if you come up with different blade designs, then the operating conditions that they work best at will change. And that's something we can control. And finally, the important input here is the solver, because we can switch between a numeric solver and an AI solver super easily. So I then go and change all of these to be ranges. So starting from the constant value that was in the documents, the engineering AI, which set up the goals, is saying, if you want to vary designs to come up with new pumps, these are sensible bounds to do that within. And that's all coming from the context that we generated earlier. And because I've got no outputs, this platform underneath automatically says, you're probably doing a design of experiments. You want to come up with a data set to look at insights and sensitivities. I'll do that for you. But what we want to do instead is generate designs that meet particular goals. So we'll set efficiency, we'll set power, we'll set the head, the pressure differential as a target. And these numbers come from those goals. So we had a constraint on power, we had a constraint on pressure, they just go straight in. And now if we change this to be foundation pump model, this will just run a study using the physics AI and generate designs super quickly. So now you can see here that this has switched from exploration to optimization, and we can start generating designs. And because this is all cloud-based, this is 5 in parallel, we can do large studies really, really quickly. So this starts generating designs, and I'll skip through, here's one I made earlier a little bit, and start to look at the output of this in a second. So the first thing we can look at here is that the design of experiments this is all simulation done with a numeric solver. And in the platform, every single one of these points is a full CAD and simulation output, and links back to the downshape and the SimScale designs. But we can just start cycling through this, and we now have this large data set of numerically solved pumps. And we can see the variation involved in this design study right here. We can go and add in the screenshot, which is an extraction of what's happened in SimScale. Again, just to get a sense that there's doing something sensible, but we don't want to be a full simulation visualization tool. You can dive into SimScale to do that if you need to. This is for managing those data sets, which is now 50 full numeric pump simulations, which you can try and export as a table if you need to, and go and do downstream training on your foundation pump models, or just export this to get insights, do sensitivity analysis, whatever. Here, it's just always going to be available and fully traceable. You always know exactly what function was run, exactly what inputs were there, and you'll never lose this data. So here we can see that there's a full table view. So I'm just going to skip for a second. So this basically is showing how, even without the help of engineering AI, but engineering AI is making it faster, we can go from study setup to get super quick insight into the problem with the DOE, and generate training data we might want to use downstream. Because like David was saying at the beginning, engineering is a data poor industry, and the ability to quickly generate large data sets we think is really valuable based on rigorous numeric simulation. But the point of this is, can we get to a pump design and a proposal much faster than we can do today? So skip forward in time slightly, I'm now seeing the results of these optimizations that I set up using the physics AI. So I've run 3, 2 of which were with the parameters I showed already. And this is a third, trying to ask the question of what if we just minimize the input power needed for a particular head requirement, because it might give something different. And as you can see here, these designs are generating quickly. So this type of question we can now ask and get a response back within minutes, whereas previously this would have been bottlenecks on probably weeks of simulation lead time. So if we go in again here and look at a plot of all the designs generated by both the numeric simulation and 3 optimizations with physics AI, they all lie on sort of the same curve. So we're seeing the same behavior being predicted by this numeric solver and the physics AI solver. And we look at the 3 different optimizations, so we can quickly get a sense of the behavior here. So the question we're asking, we could completely automate this, but as a mechanical engineer, I'm thinking this pump impeller design, if we let the blades vary, the angle vary, then we might get higher performance. But if we keep them perpendicular to the base plate, I might have a single direction of molding for manufacturability. So I'm going to ask, for this proposal, what is the design that would look like if we had a single direction for manufacturability? And what if we let the blades vary? So we can plot these 2 optimizations on this graph here, and we see this one is looking at design with the straight blades, and the one above was looking at design with the angled blades. I could see on the previous slide that you can even see more designs coming in. Each of these studies takes about 20 to 30 minutes. So in the time it takes to do 1 or 2 numeric simulations of a single pump, we get a study done that gives us an optimal design that we could take to be as a design proposal. So here I can go look at which of these designs actually meet the constraints. I've got a data set here, and all of these have got straight angle blades, and which of the ones with the curved angle meet the constraints. Sort of quickly start comparing. And then what I will do here is say, give me the best design out of the curved angle blades, essentially save this to a design proposal, compare that against the best design with the straight blades, save that design proposal, and then something I can take forward. So here we super quickly get to see these best designs, save this to, we call it collection, and then the optimization that I'm currently running that is looking at min power, we go and see where that's ending up and add that too. And it's similar in performance to the one that was with the curved angles, but we get a slightly different pump design. So fewer blades, more curvature. So we are exploring this design space really powerfully. So I'm going to add this to this proposal, name it something really cool like min power, AI. And then with these 3 designs, compare them side by side with a link that's shareable, where every single one of these is backed by a full optimization. And so we think this is really important. Like, this design proposal isn't, here's your best design, spit it out. It's, I've got 3, manufacturable, high performance, lowest input power. Like, as an engineer, what do we actually care about here? Let's take this to the person who wrote the brief, to the client, to our engineering teammate, to our boss who's saying, give it to me right now, and say, are we willing to do this? And in this case, I think there's about a 5% efficiency drop if you let the blades not vary, and we might say that's doable. So we go look in here and just like check all the data. So we have a fully configurable way of exploring what data was generated underneath every single one of these points with a full pump, full analysis. We can do this for the angled optimization and the curved optimization. And like we don't always need to dive into this. It's just if the design we're questioning where it came from, it's backed by all this data. So this is a design proposal we can get to, and this whole thing within 20 minutes. So to summarize this bit, this was the real sort of how do you combine engineering AI and physics AI to get to a design proposal. So with the setup and the collaboration between the agents that David has showed and the agent we had, the ability to run these optimizations in a platform by pulling out the models into executable workflows and get to a design proposal that isn't just one design, it's trade-offs, because that's what real engineering is about. We think this is really powerful. And hopefully it means that you can reduce the bottleneck required to get to things like this. But the final thing I want to talk about is this is building towards where this can be fully automated. So what we've shown today is it's an engineer managing it. They can do it really quickly. It unlocks algorithms that today were hidden behind experts and hidden behind emails and Python expertise. But in future, these agents we're talking about are self-improving. So the more you use them, the more an agent sets up designs, sets up these proposals, the better it's going to get at it. So you'll be able to trust it more and more in saying, here's my pump geometry. I've got this RFP. Just give me 3 designs and then write a report for them. And so this isn't an AI doing text to CAD. It's not hallucinating a pump design. It's saying, I've got better at driving a system that is generating geometry, running simulations, using physics AI, and checking all of that, and then suggesting it back to the engineer as a trade-off. There's nothing there that is like, I'm doing the engineering. It's just I'm removing all of the manual work that's normally required to do this. So this self-improvement is really important, and this is where this agent-to-agent interaction is going to be really important. And with that, I think I'd pass back to David.
Thanks a lot, Lawrence. This was super interesting. I guess we have not much more to say, but just maybe wrapping it up. Lawrence, could you once more confirm that we're looking at a blank slide right now?
Yes.
Does that work? Yeah.
Less blank.
Okay, good. And I guess just to wrap it up, because sort of we're aware what we hope could convey over the last at this point 40 minutes is that I guess like a year or two back, AI in engineering or AI in simulation was primarily about physics AI, as in predicting simulation results, and that's useful for sure and helpful in certain situations. But with the advent of having large transformer models being able to, with the right infrastructure, generative engineering's platform is also entirely cloud-based. With the right infrastructure, take advantage of big data sets, take advantage of your organization's data properly structured. It becomes possible to not just predict physics faster, but also start accelerate and automate manual work involved. And so the obvious use case is CAE automation, where an engineering team wants to sort of enable design engineers to use simulation earlier, broader, more intensely. So far, purely with templates. Now with the ability to actually have an AI reason through it. And again, the trade-offs are clear that full automation is reliable and 100% repeatable, but brittle, because it breaks apart the moment you have an input deviation. And then on the other side, you have a manual engineer doing everything manual, not repeatable. Engineering AI sits somewhere in the middle, where an AI system is able to reason through deviation, to reason through input, to make educated guesses, etc. So it has its role to play in using simulation more aggressively. And at the same, we've seen Lawrence give a gist for that, different CAD generation techniques, and that then also mixed with different optimization techniques. So again, there's many flavors of generatively creating geometry, and engineering AI is able to sort of make this, like pull this out of the expert group and make it much broader accessible. We're excited about that. In the lower left, you can see also the natural next step here is that it's not just within the software, but it can be integrated in a chat system that your organization is already using, which is the smallest step. So we're excited about the possibilities here. And I guess that, to wrap this up, we're happy to take any questions that might have popped up. And if you have any, if you're interested in sort of exploring this further, see as these systems roll out and as these capabilities are getting released, get in touch with us at SimScale, and obviously get in touch with Lawrence and the team at Generative Engineering if you're interested in the more higher level navigating design spaces and the capabilities that Lawrence has shown. Alex, I think with that, let me just say thank you, right? And thanks for spending the time with us. Again, I hope it was not just interesting, but also relevant. And I guess we have a couple of minutes for questions. Alex, over to you.
Yeah, thank you very much to both our presenters. Lots of very nice demos in a short space of time, so lots to digest. So yeah, we have a couple of questions coming in, and also just while we're addressing those, if you have any others, please do drop those into the questions panel as well. One first for Lawrence, I think, just about the demo that we just saw. So how do we validate the correctness of the AI outputs when when we're mixing like the AI results and the traditional simulation results? I think this may be something you touched on a little bit, but yeah, it'd be good to just to recap that.
Yeah, and I mean that's one of the main worries of anyone trying to adopt AI right now is how can I trust it? What are these outputs? I think there's two things. There's the way you build up these systems to make suggestions rather than like try and completely take over the role of the engineer is really important. And I think it's why we're really leaning into, you still use CAD, you still use simulation. It's just, can you remove any manual work? It essentially grounds the AI. Therefore, any suggestion it's trying to make is based on simulation data. It's based on real CAD. So that's one thing. And the second thing with the physics AI itself, because we checked here by using like a 3D surface, but you do always need to validate because physics AI isn't bulletproof. You need a lot of data to get it to be accurate. It can massively speed up, but it's also where we have algorithms underneath that can mix both. So it's not just, do I only have to use physics AI or do I only have to use numeric simulation? The real big power comes when you have the combination and you can say, use the physics AI to speed up this study, but check smartly using the right algorithms with the numeric solver, and you can still get massive speed ups by doing it that way. So that's a big opportunity we're trying to lean into.
Sure. Okay, thanks. Okay, we have another one here about data protection. So how's my data protected, and is data that's used in projects used to inform other people's projects? I guess this is possibly a question for both of you. But David, maybe you'd like to go first. Oh, are you muted?
Yeah, 5 years after COVID, you should think I can unmute myself. But the basically no change to how data is handled on SimScale before. Data is never shared with anybody else. Data is always sits in the team account of an engineering team, and it's the same whatever is trained from it, be it a physics AI model. In fact, the permissions to access a simulation project inside your organization is the same permission management for physics AI model. So if you've trained a physics AI model, it's the same where you can you decide who gets access to that physics AI model. In one step further, you can see. And I guess this is a bit the unique aspect on having all of this cloud native. You can see and trace back which data was used to actually train a certain physics AI model, and all of that sits within the team account of an engineering team on SimScale. And the same with engineering AI. What we're providing out of the box, again, I earlier called it a junior engineer, is a pre-configured, a pre-trained transformer model that is being done on public data, and hence it only knows the internet and how to use SimScale and how to has seen public simulation projects. But in order for you to apply it to your specific engineering workflows, to your specific simulation workflows, that comes from your data. And again, also here, same story, never shared with anybody else.
Great. And yeah, Lawrence, do you have anything to add? I'm sure it's a question you often get as well.
Yeah, it's very similar. I mean, our platform also is able to run over local models and local environments. So this is something we think is quite important. So if you want to host everything on your machine, we are building towards that. But yeah, like David said, anything that's in the cloud there's no change in that's only yours. There's nothing trained on that. What the self-improvement is the system gets better and better at just driving the generative platform, and there'll never be any sort of cross-industry training, cross-company training.
Sure. Yeah, and then one more maybe about on the physics AI side for you, David. So we've heard about physics AI models, and also we saw a foundation model used in the demonstration by Lawrence. And so the question is how do people obtain those models, or how do they create them? How do they get access to those
I guess we don't have time for another demo anymore, but if you have, so that's the same, you use the word, foundation model. The physics AI capabilities in SimScale are natively integrated, and if you're having access to it, it sort of shows up in your dashboard on the left as AI models, and there's like your, the AI models you have access to. And same here, as your organization sort of, trains a new AI model, selects certain simulations that your team ran, it produces physics AI model accessible to you. We, as a SimScale team, are using the exact same technology to effectively build public physics AI models based on public data, no customer data, public information, and we're pre-training these models with the intent to lower the barrier to start exploring these types of technologies. And then sometimes the use case for this is, and again, it's used the exact same technology, the exact same stack. It uses the robustness of the data management and a tight control between sort of how you feed the data into training and how you deploy the model, yada, yada, yada. So it uses all of the same technology and has the, brings the advantage for a customer to be able to explore this quickly. So in the best case scenario, to actually have a zero-shot inference that actually works, where out of the box, it's reasonably accurate for an application that the customer has, but mostly to train on top of it, to have a pre-trained model that you can use as a basis for further training. But again, I guess like the important part of the answer here is the fact that this is a single stack, it's a single technology, it's a single platform where all of this is integrated, and we as a SimScale team are using the same technology to just supply sort of helpful models out of the box that customers don't sort of need to start from scratch. And those models are always done on public data, on publicly available information. And as customers start leveraging that, they are feeding it with their own private data that nobody else has access to. And by the way, maybe Alex, if you're calling it foundational model, pre-trained model, I guess like the industry is still figuring out what it's gonna call it, and how broadly and how generalizable these models will become. We'll see. Right, sure is that it's going to need a lot of data, it's going to need a lot of compute, and so my bet is on the fact that it's going to be in the cloud, I guess.
Sounds good. All right. Well, thank you very much to our presenters and to the audience, all the questions. I think we'll leave it there for today. Give people a chance to get ready for their next meetings and the next tasks. So yeah, let's close the session. Look forward to speaking to you next time.
Thanks, everyone.
Thanks, guys.
Bye-bye.
Thank you. Goodbye.